All right, let's get right into it. Today, we're looking at something huge, a bold new claim in science. A new paper says it has solved the hard problem of consciousness, and not with philosophy, but with math, with geometry, of all things. I mean, just think about that for a second. What if the feeling of being you, the experience of seeing red or hearing a song, what if all of that could finally be described with the same precision we use for something like gravity? That's the idea here. And if it's right, it changes, well, pretty much everything.
So here's the game plan. We're going to break this down into 5 parts. First, why has this problem been so tough for so long? Then we'll get into the wild geometric solution they're proposing. After that, we'll look at the specific rules a system has to follow to be conscious. Then comes the really cool part, 4 things this model actually proves mathematically. And finally, we'll talk about what this means for the future of things like neuroscience and AI.
Right, so for basically all of human history, consciousness has been this slippery thing. It's been left to philosophers, to mystics. Science has had a really hard time even getting a grip on it. And the reason why is that we've never had the right language, a language precise enough to actually describe our own inner world. And this quote just nails it. The authors are arguing that consciousness isn't magic or some mystical force. No, the problem is that our tools were wrong. We've been missing a formal, mathematical way to define what it is we're even talking about. And you can see the huge leap right here. Old theories tried to say consciousness was just a side effect of something else. It's just brain stuff, or it's just what computers do, or maybe it's everywhere, in every rock. This new model says, nope, consciousness isn't a byproduct, it is a specific thing, a particular kind of geometric structure made of information. It's an object we can actually define. Okay, so if consciousness is a geometric object, what does that even mean? Well, this is where the paper drops its big idea, its central concept, the information manifold. So, what is an information manifold? Think of it as a very special kind of data structure. It's so interconnected, so deeply woven together, that the whole thing is genuinely more than the sum of its parts. You can't understand it by just looking at the pieces. And here's the kicker. It has to contain a smaller, simpler model of itself, inside of itself.
Now this is the definition. And it's not just a nice-sounding sentence. The paper actually presents this as a mathematical equation. It's saying that your actual experience, right now, is the output, the stable projection of this deeply integrated, self-modeling, geometric thing that is constantly and smoothly changing. Okay, so obviously not everything is conscious. My coffee cup isn't conscious. So for a system to count as one of these information manifolds, it has to play by a very strict set of rules. And these rules are specifically designed to line up with the things we all know about our own experience. And there are 4 of them, 4 non-negotiable criteria. Its information has to be integrated into a single whole, it has to have continuity through time, it must be self-referential, and it has to project its internal state outward. Let's quickly unpack what each of these means.
First up is unity, or integration. Your experience right now, everything you see, hear, and feel, it's all one single unified whole. You can't just surgically remove one part of it. If you tried, you'd break the whole experience. The model says that's because the manifold, mathematically, can't be broken down into separate pieces.
Second, continuity. Pretty simple, right? Your consciousness flows, it's a river, not a series of disconnected snapshots. One moment blends seamlessly into the next. In math terms, that just means tiny changes in time lead to tiny changes in the manifold's shape. No sudden, jarring leaps. Third, and this one is a bit of a mind-bender, is self-reference. The system has to contain a model of itself. It's not just thinking about the world outside, it's also thinking about its own thinking. It's this recursive loop that allows the system to, and I'm quoting here, learn itself. This is their mathematical foundation for what we call self-awareness. And finally, we have projection. The idea here is that the rich, complex, high-dimensional reality inside the manifold can't be fully seen from the outside. Anything you could measure, like with a brain scan, is just a shadow of what's really going on inside. And this, right here, is a beautiful explanation for the privacy of our own minds. Nobody knows exactly what you're feeling because they can only ever see the shadow, not the real thing.
So the model lays out these 4 rules. That's the setup. But here's where it gets really powerful. Once you accept those definitions as your starting point, the paper goes on to formally prove the answers to some of the oldest, thorniest problems in the philosophy of mind.
It doesn't just suggest these things, it proves them. It delivers 4 key theorems. And this is the real accomplishment, you know? It's about moving the conversation about consciousness away from endless philosophical arguments and into the world of formal mathematical results. So here they are, the 4 big proofs. It proves unity, because the manifold is mathematically indivisible. It proves privacy, because any measurement from the outside is just that lower dimensional shadow. It proves identity, that feeling of a stable you over time, because the manifold's geometry persists. And maybe the most shocking one, it proves substrate independence. It doesn't matter if it's built from neurons or silicon chips. If you build the manifold, you get consciousness. The material doesn't matter, only the structure does.
And I really want you to let that sink in for a moment. Inside the world of this model, these aren't just cool ideas to debate. They are mathematical facts. They're as certain as 2 + 2 = 4. This is what it looks like when a field goes from pure speculation to a formal theory.
Now, a theory can be beautiful on paper, but the real question is, can you test it in the real world? And that brings us to the final and maybe the most critical part of all this. What does it actually mean for science? Well, the model makes very specific, testable predictions. It says we should be able to find unique mathematical signatures of this high-level integration in our brain activity. We should see our brain states moving along smooth paths, not just jumping around randomly. We should be able to find real evidence of the brain's own self-model. And we should even be able to measure how much information we're losing when we try to scan a brain from the outside. All of these are things we can actually go out and test today. And of course, the implications here go way beyond the human brain. Because as we build more and more powerful AI, there's this one question that's becoming incredibly urgent. Could an AI become conscious? And how on earth would we know if it did? This is exactly why a formal model matters so much right now. We absolutely cannot risk having an AGI just guess whether something is conscious based on how it acts or what it says. That's a huge safety risk. We need a real, rigorous mathematical test. And this table just lays it all out. The human brain seems to check all the boxes. The AI we have today, like the large language models, they absolutely do not. They're not integrated, they're not self-referential in this deep way. But a future AGI, well, that's the giant question mark. And the amazing thing is, for the first time, we might have a formal checklist we can use to actually find the answer. The paper ends with just these 5 words. Now the manifold is defined. It's so simple but so powerful. It feels like a turning point, the moment when a timeless mystery might have finally been reframed as a solvable problem. The hard problem isn't solved yet, not by a long shot, but we just might, finally have a map.